My name is Nicole Carlson. My pronouns are she, her, and hers, and there's my email and Twitter handle if you want. And today I'm going to be talking to you about a PySpark cautionary tale entitled How to Spend 3/4 of Your Yearly Budget in 3 Weeks. And it's actually even worse than that. It's how to spend 3/4 of your team's yearly budget in 3 weeks, not just the money that's allocated for you. So the way this talk will work, I'll tell you about the problem I was trying to solve, the disaster that took place, and what I should have done differently. I work for a company called ShopRunner. We're an online network of about 140 retailers, including companies like Newegg, Staples, Saks Fifth Avenue. Our members get free 2-day shipping and free returns from our partners. And as a company, we add code to the retailer websites, and we provide them with marketing tools like personalized emails, out-of-stock notifications, a bunch of different stuff. I actually have free membership cards, so come see me afterwards if you want a free 1-year membership. Since we're in the retail space, one of the first projects for the data science team was to come up with some way to recommend similar products. So in this example, if somebody has viewed this kick boot jean, we want to be able to recommend other products we think they'll like. And we decided to start with a relatively simple approach, which was cosine similarity based on orders data. So our orders data lived in a database in a table roughly like this. So one column is the members, the other column is the products that they purchased. We then take this orders data, read it in from the database, and work in Spark. So once we have this orders data, we turn it into a member-product interaction matrix. The rows are the members, the columns are the products. We put a 1 where somebody has bought that product, a 0 otherwise. So you might imagine this ends up being a pretty sparse matrix because most people do not buy most things. Then the way we find similar products is by comparing the columns with one another. And the specific measure we used was cosine similarity. So you can imagine that these columns live in a high-dimensional vector space where the dimensionality is the number of members, and then you compare the angle between them. If they're pointing the same direction, the similarity will be 1. If they're at right angles, the similarity will be 0. And since our interaction matrix was only made of 0s and 1s, our similarities will only be between 0s and 1. We won't have any negative values. This graphic is from a blog called Data Aspirant by somebody named Saimadou Polamiri. Kung Fu Panda has nothing to do with the rest of the talk. I just really like this graphic a lot. So as I mentioned, my company was using PySpark. We have a lot of data. We knew we wanted to work in parallel. And in particular, we use PySpark on top of Databricks. Databricks is an online platform for running Spark clusters. They have their own notebooks you can run on top of them, and you can schedule jobs, and there's some other nice features. Our data lived in Snowflake, which is a new relational database, and some of it also lived in Amazon S3. So I worked on this with my coworker Hannah, and first we did all of our work in a Databricks notebook. Then when we were satisfied that everything was working the way we expected, we put it into a nice Python package, with classes and functions and all your favorite Python stuff. We're good Python programmers, so we wrote unit tests. Hannah's actually giving a talk about unit tests in a few sessions. You should check that out. So we had good code, we had unit tests, we had our cluster ready to go. So we were ready to find similar products by orders. And it worked really well. It worked great. I think better than anybody on the data science team expected. So here you see those same kick boot jeans, and you see that we're recommending other kick boot jeans, other types of pants, top, but they all kind of look like they're the same style, so it looks pretty good. And we were super happy about this, but one issue with orders is that some products are never ordered or very rarely ordered, so we can't recommend other similar items for those products. So for our next iteration, we decided to use member page views. So since we have code on our partners' sites, we know what products our members are viewing. And most people view a lot more products than they actually purchase. So it's the same general structure. We have some data where one column is members, the other column is the products that they viewed. And in our case, this was about 1,000 times larger than the orders data. So we're feeling pretty good about this. Our code was still in the Python package. still unit tested, we had our clusters ready to go, and at this point, the code had been functionally tested with orders. So we were pretty confident that it would be super easy. So all I had to do was use a new data source. Hannah and I wrote this similarity job class, so that it was really flexible. We knew we were gonna have to do a bunch of these types of jobs, so all I had to do was swap out the data source. So orders for member views. No problem. Very easy, right? No! Turns out it was not easy. So this data set was much larger, and the job was taking a lot longer to run, like 8 hours. And all of a sudden, I started getting this super weird intermittent PySpark error that I did not understand at all. Sometimes it would happen like an hour into the job, sometimes 4 hours, sometimes 7 hours, sometimes it would be the very last step, which was super painful, but I had no idea what was going on. If you haven't seen a PySpark stack trace, they're pretty gnarly and terrible, and I'll let you live through that with me. So, you get back a bunch of stuff from all the workers and the driver, and I don't think humans can read it. You probably have to be a robot, and they just go on and on and on and on and on. And actually, you can see at the bottom, it says one more. So the stack trace is so long that they can't even return it all to us. So obviously, I had no idea what was happening. This is impossible for a human to read. The part of the stack trace that seemed relevant to me was this thing, the provided token has expired, something about S3. So as I mentioned, some of our data lived in S3. So I assumed that for some reason, we're hitting some limit that we hadn't seen with orders. And I thought, well, I guess I just have to make everything faster so we don't hit this limit. So here were the ideas I came up with to speed things up and avoid the S3 timeout error. I was pretty new to PySpark, so these are kind of my naive ideas. So my first idea was just run it again. And I kind of hoped that the problem was with Databricks or AWS and not my code, and that miraculously everything would just work. I also thought maybe there's so much more data that I just need to add more nodes and somehow this will fix everything, right? More nodes, more parallel, great. I also considered increasing the individual node size. Maybe the nodes just weren't powerful enough for some reason. I don't know. And maybe I should just try all of this at the same time and everything will be great. I wasn't a complete fool though. I know that PySpark clusters cost money, more than just running stuff on my laptop. So I went to my boss, explained the problem. I have witnesses to this conversation, and one's in the front row. And so I was like, hey, this is what's going on. These are the ideas I have. So, how big can my clusters be? And he said, as big as you want. Don't worry about it. Like, there's no way you're going to spend too much money. Like, we have to solve this problem, so just go for it. This is a giant carrot in New Zealand. It's the primary reason I went to New Zealand. I highly recommend you check it out if you're ever there. It's amazing. So, had a bunch of ideas, had permission to spend a bunch of money. Everything was looking good. 3 weeks later. So, this is a graph of our cluster usage over time. As you may have guessed from this graph, I was working on this in March. You can see that I spent way more money in March than in any prior months or any subsequent months. And again, this is the team budget, not just the money that I was spending. So I think the first lesson to take from this is if your boss tells you you have unlimited resources, they're wrong. It's not true. It doesn't matter where you work. If you're at a 2-person startup, if you're at Google, if you're running that 10,000 node cluster they mentioned this morning in the Julia talk, there's some upper limit. And additionally, at one point, my boss told me that I was spending $72 an hour. But the problem was I had no idea what that meant. Like, is that a lot or a little for clusters? I have no idea. So along with realizing there's an upper limit to how much you can spend, you should figure out what scale of cost is appropriate for your company. And if you're a manager, you should definitely impart this information to your employees. Otherwise, you're going to have to make graphs like this in the future. All right, so what should we have done? I was pretty new to PySpark when I was working on this. Now that I'm 6 months older and wiser, I realize there's a number of things we could have done differently. So the rest of this talk will be me giving you some PySpark suggestions, and at the end I'll explain the actual error that we ran into. All right, first suggestion is pretty simple, and that is check on your cluster and database usage. So here you can see a Snowflake bot or data engineering team set up. Every day it messages the data science team, tells us how many credits we used, how many credits we have remaining. They set this up in April. I'm sure that was entirely coincidental to me spending the money in March. So if you can, set up automated reports like this. If you can't, just set a calendar reminder, just check. It may seem like kind of a waste of time, but had we even checked a week into my spending spree, we still would have saved a significant amount of money. I wouldn't have had a talk, but the company would probably think that was better. All right. Another thing I should have done was test with a smaller data set. I was feeling really good after the orders worked super well, so I figured I should just throw all of the member page views at the problem. And I think this is something a lot of data scientists do. We have this fantasy that the very first model we run will work perfectly and we won't have to make any adjustments, so we might as well just throw everything at it the first time. I don't know why I believe this. It's never true. It's never been true for anyone, but I still want to do it. With Spark, that's a really bad idea though, because your data size can matter a lot. The same code that works with a smaller set of data may not run with a larger set. You may have to change things around. So it would have been better if I had started with a subset of the member views and slowly scaled the data up to make sure the code was working the way I expected it to. All right, this one's really particular to PySpark, and that is partitioning your data appropriately. When we started out with orders, we were just using the default values for Spark. So when you read in some data, Spark decides how it wants to partition your data. It seems to be based on the number of files, how many workers it has, some mysterious formula. In a lot of cases, it works really well, but when you get to larger sets of data, it doesn't always do a very good job. And the suggestion we've heard from Databricks is to not have more than 256 megabytes per partition. So you can use a formula like this. So first, figure out how many megabytes you have per row. This is if you have growing data, right? Every day people are viewing more products, so we didn't have a static number of rows. So cache it, save it to disk, to memory, whatever. Figure out how big your data is. Multiply the number of rows times megabytes per partition, and divide by the max megabytes you want to have per partition. So relatively straightforward, but something you may not be aware of as a new PySpark user if the defaults have just worked well for you in the past. All right. Another thing I didn't realize is that good Python code can be really hard to debug in PySpark. So here you can see the code from one of our similarity jobs. First, we instantiate an instance of that similarity job class. We generate the recs. We call the write recs to DBs method, and everything is done. That's the whole job. And it's so beautiful. It's so elegant. It's so simple. But if there's a problem, you're going to have no idea what's going on. There's a ton of logic packed into each line of code. So if you run into errors, like super gnarly ones that you can't figure out, I would suggest that you unpack all of your nice functions and classes and run each line of code separately in a notebook. This kind of feels counterintuitive and it feels wrong after you spent all of the work trying to make everything nice, but it will actually save you time in the long run. And it's something my boss always tells me to do, and I always resist, and then a week later I end up doing it anyway. So learn from my mistakes and just do it right away. And in particular, with PySpark, you're going to want to run each step separately when you're debugging. And I'll go through this example in a minute. But the reason why is because Spark does something called lazy evaluation. So when you call a transformation, like multiplying two columns or capitalizing a string column or whatever, it's not actually executed until some action is called. So one common action is count, like figuring how big your data frame is. Another one is take, taking a row from your data frame, collecting stuff to data, whatever. So if you set up a bunch of transformations and don't call an action, Spark tries to optimize everything so that all of the transformations are run in the best way possible. And sometimes this works out really nicely, and sometimes it makes things really confusing. So on the left, you can see that I'm taking some data frame, df, I turn it into a coordinate matrix, I turn that into a row matrix, and then I call column similarities on that row matrix. The red indicates that there's an error. So it looks like there's an error during this map tuple phase. On the right, you can see I've split all of these steps out. First, I turn the data frame into a coordinate matrix. I take a row from that, and it works. So that's an action, so things are executed. I then take that coordinate matrix and turn it into a row matrix, try and take a row from that, and that's where the error is actually taking place. So if you don't execute your transformations, it can be very hard to figure out which one is actually causing the issue in your code. And this is another thing that feels kind of wrong. Like, all you really care about is the last step usually, so you're probably like, well, why do I need to execute all these things? I don't really care about them. Because it will save you time and money, right? It'll just make your debugging a lot easier if you can be sure that each line of code is working the way that you expect it to. Similarly, I suggest that you save intermediate steps to Amazon S3 or whatever other cheap storage space you have, HDFS, I don't know, Google probably has something. So writing to S3 is an action like count or take, so that will cause your transformations to be executed. And if you save your intermediate steps, you'll have them to look back on later, especially with super long jobs that may run overnight. So for example, the first step in our similarity job takes like 2 hours to run. So if there's a bug and we come in the morning, we don't want to have to wait 2 hours to get to that first step. So if we have a bunch of intermediate steps saved, we can immediately start debugging and make sure that things are working the way we want to. And this is another thing where it may feel like you shouldn't be wasting the storage, but it'll save you debugging time, and S3 is pretty cheap, so why not? Okay, let's switch gears a little bit and talk about JDBC connectors. JDBC stands for Java Database Connectivity. It's an API for how Java clients access databases. So when you're working with PySpark, Spark will try and get data from the database. It'll send the request through the connector. The connector will talk to the database, and the database will send the data back through the connector. And one issue with JDBC connectors is that by default, most of them will just open one connection. Obviously, this is not very useful for Spark because a bunch of your workers will be sitting around idle. So you have to manually control how many connections you open. But if you open too many connections, you're going to be hammering the database, and that's going to cause its own problems. So we talked to Databricks about this, and at first they just said, don't use JDBC connectors ever. Obviously, that's not practical for a lot of us who use databases. So their second piece of advice was to remove JDBC connectors as soon as possible by saving your data to S3. So here on this slide, you can see I've loaded some orders data from Snowflake. I immediately write it to S3, and then I read the orders back in. And from then on, we work with the read-in orders data frame. And I haven't really seen this piece of advice in any documentation online. I'm not sure why. It seems super important, and I feel like everyone should know about it. But just cut out your database entirely. Get rid of the connector as soon as possible. So now whenever my team runs PySpark code, we immediately write the results to S3 and they read them back in before doing anything with them. All right, at this point you may be wondering what was causing that S3 expired token error. And had I followed the 6 suggestions I've given you so far, I actually would have sidestepped the error entirely. I wouldn't have seen it at all. So I never would have figured out what was going on my own, and actually we had to work with Databricks to understand what was happening. And I didn't want to use the same graphic, so I flipped it. I thought that'd be different enough. All right, so the secret to what happened is buried in that gnarly stack trace I showed you earlier. I don't know if any of you caught it. Maybe you're really good at reading stack traces. So here you can see within the stack trace, there's something about Snowflake. When I told you about the job earlier, I mentioned that the first thing we did was read the data in from the database, and then all the calculations were in Spark. This error was coming up 2, 4, 6 hours into the job, so Snowflake should be gone by then. Snowflake shouldn't be doing anything. All of the errors should be involved with PySpark. And it turns out there's some issues with the Snowflake JDBC connector. And one way we can see this is by looking at caching. So first, I'll show you how Spark caching is supposed to work. Here I have some orders data that's been read in from S3. On the bottom, you can see I've called cache on it, and this command takes no time at all. So with cache, you're basically just telling Spark, hey, the next time you use this data frame, save it to disk or memory so that it doesn't have to be recalculated again. So the next time an action is called on it. So it is a a lazy operation, right? Nothing should be happening at all. And this is the way we expect things to work. In contrast, let's look at caching on data that's been read in from the Snowflake JDBC connector. So I've loaded in that orders data, and then I call cache, and you can see this time the command has taken 45 seconds. And that should confuse you. That doesn't make any sense. So as I mentioned, that's a lazy operation. It should take no time at all. And what we discovered is that the Snowflake JDBC connector confuses the Spark optimizer sometimes and causes it to read in the data multiple times, even when it shouldn't. So the connector will keep re-triggering database calls even when it's already read in the information. At this point, you may think, well, that's fine. That would kind of suck. It would just make your job run longer, though. So, we read the data in, we get 6 hours into the calculation, then all of a sudden it decides to read it in again, and then it goes through all the calculations again. That's not fun, but it will just take a longer time. But it turns out that additionally, there was a secret S3 temp storage timeout that Snowflake had set. And this was a setting that Snowflake controlled entirely. Our admins had no way of seeing it. And when you're trying to pull data into PySpark from Snowflake through the connector, it turns out that Snowflake temporarily stores things in S3. So we were reading the data in, our calculations were taking a super long time, and so we're hitting their 60-minute timeout that we had no control over. So this was the actual underlying cause. So their connector was causing rereads from the database, and their temp storage had a timeout that we had no control over. And so all of a sudden, at different points in my calculation in our job, we would be hitting their S3 timeout error. So my final piece of advice for you, if the first 6 don't work and you still have weird errors, is to ask your vendors if they have any unexposed settings, for example, timeouts. This can feel kind of contrary to regular Python coding. So usually you trust your connectors, you trust third-party libraries. But in our case, we're working with Snowflake, and they're a very new technology. So it's not surprising that their code has some bugs. We all have bugs. And when you're working with this really new stuff, you often have to code more defensively than you would otherwise. And in some cases, there may be settings that they haven't realized that their end users might need access to. So it's worth checking out if there's anything like that. Work with your vendors. I'm sure they want to keep your business and want to keep you happy. And hopefully you can solve some of your gnarly bugs. All right, so just to recap, here are the suggestions I have for you. 1, regularly check on your cluster and database usage. This is kind of a no-brainer. Just do it, even if it feels like a pain. Test with a smaller data set, especially if you're working with PySpark, because you'll end up saving money and being able to debug your code more easily. Partition your data correctly. And again, the advice we've heard from Databricks was no more than 256 megabytes per partition. Run each PySpark calculation step separately, so trigger your transformation so you can make sure everything is happening the way you expect it to. Additionally, save your intermediate steps to S3 so you have them later to look at. If you can, avoid JDBC connectors. If you can't, try and get rid of them immediately by writing your results to S3 or some other cheap storage. And finally, if these 6 things don't work, then work with your vendors and check for any unexposed third-party settings. For example, secret vendor timeouts. So you may think this is kind of a downer of a talk, but it has a relatively happy ending. This is our CFO, Ozan. Ozan worked with my boss to get a chunk of the money I spent on Databricks back from Snowflake, since it was ultimately their timeout that was at fault. And they did this by threatening to go back to Redshift, which is my favorite part of this whole story. All right, so thank you all for listening. Thank you to ShopRunner for letting me spend a bunch of money and then paying me to come talk about it. Thanks to the data science team, Michelangelo, Hannah, Ali, Rishi, and Scott. Some of them lived through this with me. They all gave me feedback on the slides and the proposal. Hannah and Ali are talking later. They have really good talks too. Tutor Radoka also helped me with the proposal and slides. Thanks. Questions, I guess?
I have a question. Why are your EC2 limits so high?
What?
You should never have been allowed. You could easily set down the EC2, not let it create that much spend. You're managing spend really early in the stage, but not allowing somebody to spend. There's limits to that.
Well, we were working with Databricks, so we weren't controlling our AC2.
I mean, I'm saying like there are limits in these cloud providers that protect you from that problem. It's not unbound.
Right, but I mean, he didn't think I was going to spend too much.
But you should always think. You shouldn't just let you can't just allow unfettered access to the cloud as a service and not expect them all to have.
I guess I haven't set up a cloud team.
I mean, there's other ways to prevent the problem.
It was a lesson learned from a very young data science team. We just started working on this.
Yeah.
Yes, there's a lot of things we could have done differently.
It's a lesson learned.
Yeah.
If Snowflake didn't have the 60-minute setting in place, wouldn't you have just kept spending that money or something like, or like having jobs run forever?
Yes.
It seems like that was a decent limit to set.
Yeah, so having that 60-minute limit in place actually helped us figure out what the bug is. So you're right, we would have just kept spending money. Our jobs would have finished though. So at one point they did increase the limit for us, and I was able to get a job to finish. And then we also started doing like this writing to S3 stuff as well. So it's based on real events, maybe not in the exact sequence they happened. Yeah.
I maybe you're missing something. And Snowflake suggested that you didn't use the JDBC connection.
Databricks.
Databricks. Okay.
Yeah.
I was going to ask what were they suggesting you use instead?
Well, so Databricks just told us to immediately write to S3 and then work with the data from there.
So they were saying just use it once rather
Yes.
than don't use it. Okay.
Well, initially they told us not to use the connector, but obviously that's not practical. Cool. All right. Thanks. I'll be around.